Unit 6, Day 2, Key Features of Polynomial Functions. This is Mr. McGough up in R12. Let's start off with a little bit of review. So we're looking at this function that's graphed, and we're trying to see which function describes what's happening here. So the first couple of things we can see. We see our zeros at x equals 3 and x equals 6. So we know that at least part of our function is x minus 3 times x minus 6. So we can eliminate b right away. The next thing we see is our vertex. Well, we can find our x value for our vertex by taking the average of 3 and 6. That gives us 4.5. That is our axis of symmetry and our x value for our vertex. We look at our y value for our vertex. Let's zoom in just a little bit. So counting down, 1, 2, 3, 4, 5, 6, a little more than 6, but a little less than 7. So it'd be negative 6 point something. And that's going to matter. So if we take our vertex value for x, our axis of symmetry value, we can plug that in to our factored form. So 4.5 minus 3 times 4.5 minus 6. 4.5 minus 3 is 1.5. 4.5 minus 6 is negative 1.5. Quick calculator work. If I can fit it in the square. (1.5) times negative 1.5 equals negative 2.25. Well, let's see. I need negative 6 point something. Is it possible that's actually negative 6.25? Well, let's see. If we multiply this by 3, that would give us that output value. So that means what's really happening is that our function factors also have a greatest common factor of 3, which will give us that negative 6.75 we're looking for. So that means that our answer for our review problem is D. Let's move on to our second review problem. Here we have a water balloon is launched upward from an initial height of 15 feet and an initial velocity v0 of 50 feet per second. The height of the water balloon can be modeled by the equation as given, where t is the time in seconds and h is the height above the ground. Find the time it takes for the water balloon to hit the ground level and round your answer to the nearest hundredth. Let's write out our equation with those values for v0 and h0 put in. So we'll get h of t is equal to negative 16 t squared plus v0 is 50. So 50 t plus h0 is 15. This looks like a good job for the calculator. So let's go ahead and grab our graphic calculator out. And we're going to start by putting in the function. Negative 16, I used x instead of t, but negative 16 x squared plus 50x plus 15. Now, one thing I had to do is I had to change my window settings. I want to make sure that my graph is actually going to fit. So if you haven't done this before, you can go in and set your window settings. I used x min. Since x is time, I used a minimum of 0 seconds, and I went out to a maximum of 5 seconds. I did actually do this offline, so I could see what would fit best in the window. Y min, the minimum height will be 0, because that's when it hits the ground. And Y max, I just picked 100. I'd started out actually larger than that, but I wanted to get a good picture. So again, I adjusted those offline. Now let's go ahead and hit graph and see what this looks like. So here's our launch of our water balloon. We see it launches from 15 feet off the ground, it arcs up, and then it comes down to the ground. The question asks us to find the time it takes the water balloon to hit the ground level. That will be a 0 at the end of our graph. So let's take a look at our table. So on our table, when x equals 0, when time equals 0, we start off at 15 feet. As we go down, we see that it reaches an apogee, and then it descends, and then somewhere between 3 seconds and 4 seconds, it hits the ground. So we can go into our calculator, or calc, and we're going to find a 0 value. We'll select that. We'll move our arrow over for our left bound. Hit enter. We'll move our arrow over for our right bound. We'll go past that point. We'll hit enter. And then we'll ask it to guess. So we get y equals 0 at 3.40 seconds. Now, we could also do this mathematically. We could say h of t equals 0. That is our height of 0 when it hits the ground. Equals negative 16 t squared plus 50t plus 15. We can use our quadratic formula. Negative b, negative 50, plus and minus the square root of b squared, 50 squared, minus 4 times a times c, all divided by 2 times a. Now when you do this, you'll see that you'll have one value where x is, or t, is less than 0. So that would be, if you started essentially time before you got up to 15 feet high, would be the other side of that arc. If we look at our graph, it would be to the left of the y-axis. And then our second value will come out to the right of the y-axis. I'll leave it to you to go ahead and crunch through the quadratic formula. Now our new information. So we're going to be looking at a bunch of different types of polynomials, not just quadratic functions. So end behavior we've discussed before. That is what occurs as x approaches negative infinity. In other words, if it's going left, there's an activity that f of x will go towards. The other end, as x goes towards positive infinity, f of x will go towards something. Those are the ends. It's essentially the arrowheads at the ends of your graph. Increasing or decreasing intervals on our graph. If our graph is going downward, that is a decreasing interval. So here and here. So decreasing interval is when our graph is decreasing over some span of the domain, the x values, or our slope is negative. Positive, increasing intervals. Well, increasing intervals are where our graph is increasing. In my example, that's in the green. Positive and negative intervals. Positive intervals are when f of x is greater than 0. In other words, above the x-axis. And our negative interval is when f of x is less than 0, or below the x-axis. I'm using x-axis because x-axis is where f of x equals 0, or y equals 0. A relative min or a relative max. Well, if we take a look at our graph that we've been using here, we'll see that our end behavior on the left as x approaches negative infinity, it goes off to positive infinity. But I have a relative max to the right, where the function itself increases, pauses for a moment, and then decreases again, and that is called a relative max. So it is a place on the graph other than the end behavior where the graph has a max or a min. So think about that for a moment. When we had our parabola, we only had one place. That was a min, or if it was pointing downward, a max. But now we can have a function that has multiple local maxes or local mins. Next part of your notes. An odd degree. The end behavior is going to be in different directions. An odd degree means that your highest power is an odd number integer. If your leading coefficient is positive, you'll have a graph whereas x is positive, the graph goes off to positive infinity for end state behavior. If your leading coefficient is negative, you will have a graph whereas x goes positive, your graph itself heads off towards negative infinity. Even degree. When you have an even degree function, in other words, your highest power is even, 2, 4, 8, then your end state behavior will be in the same direction. If we just use our parabola that we've already learned as our example, because it has a power of 2, if we have a positive leading coefficient, our ends both point upward. As x approaches negative infinity, end state behavior as it goes to positive infinity. As x approaches positive infinity, end state behavior as it goes to negative infinity. If we have a negative leading coefficient, our ends will tend downward, and therefore, same direction, both of your end state behaviors will be towards negative infinity. When we take a look at number 1, we have a negative leading coefficient. Our highest power of x in the first factor will be x to the 5th. In the second factor, it'll be x to the 3rd. That means our highest power will end up being, well, we'll add those two powers together and we'll get x to the 8th. So it would be an even degree with a negative leading coefficient. So as we look back to our notes, we see that our end state behavior will be as x approaches negative infinity, f of x will approach negative infinity. As x approaches positive infinity, f of x will approach negative infinity. So here I've gone ahead and put in our graph. I've had to change my window significantly because my y values get very large and very small. And now let's graph it. And what we see here is it comes up from below, turns, peaks, comes down, flattens out, and then heads back down south again. So if we thought about this as our graph comes up, spikes, and then heads back down. So our behavior is as expected. It heads down towards negative infinity as x goes to negative infinity or as x goes to positive infinity. Now, on to problem number 2. You can back up if you need to take a look at number 1, but something happened to my screen and it was blocking. So number 2, we're going to go ahead and we're going to put in this function into our calculator. So negative x cubed plus 2x squared plus 2x minus 1. From there, we can graph it. We'll take a look. So we see that this graph has 3 zeros, and the end state behavior as x goes to negative infinity, it's positive infinity. As x goes to positive infinity, it's negative infinity. That's because of that negative leading coefficient. Now, from our calculator, we can bring up a table. When x equals negative 3, f of x equals 38. At negative 2, it's 11. At negative 1, it's 0. At 0, it's negative 1. At 1, it's 2. At 2, it's 3. And at 3, it is negative 4. So let's plot those points. Well, we can't really plot negative 3 comma 38, but we know it goes pretty high. Negative 2, 1, 2, 3, 4, 5, 6, 7, a little too high still. At negative 1, it's 0. We know from there stretch. It goes rapidly upward. Oops, way upward. At 0, it's negative 1. At 1, it's up to 2. At 2, it's at 3. And at 3, it's at negative 4. So generically, that's the picture of our graph, which matches our graph. Now, I did also change my Windows setting yet again. So this is skewed because my x is only between negative 5 and positive 5, and my y goes from negative 20 to positive 20. So if I use the same scale as on this graph paper on my screen here, then it'll look the same. So for the next several problems, I'm going to do most of the work offline, but I'm going to show you how I do it. So I've given f of x. I put it into my calculator as y equals, I put in the function. And then I can check the graph, and then I can go and look at the table. From the table, I'm going to go ahead and create a t-table and plot my graph onto the small graph paper on your note sheet. And then from there, I'll identify increasing, decreasing, positive, and negative areas and the end behavior. So I'm going to click back and forth, and what you'll see is just suddenly the screen will be filled with the next information. So please go ahead and put this equation in, get your graph, get your t-table, plot your points, and I will do the same. So now I have gone ahead and taken a look at all of my local max and min, which I can find using my calc function to find a minimum or a maximum. So for example, to find a minimum, I would hit the minimum. I would go to the left of the min. Here we see a min. I would hit enter. I go to the right of the min, hit enter, and then it says guess. So my local min at that point is 0.364, 0.76. You can do the same thing with your local max. There's two of them. And then you also have the ability to go in and find your zeros. Again, we go to our second calc function, we go to the zeros, and we go to the left of one, hit enter, go to the right of it, hit enter, and ask it to solve. So negative 0.777, so negative 0.78 is a 0, and 2.92 is another 0. So from there, we can then take a look at getting our increasing and decreasing. So I'm going to highlight in green my increasing. I am increasing from negative infinity to my local max at negative 0.31. So from negative infinity to negative 0.31, approximately. And I am increasing from my local min at 0.364 up to my local max at 2.198. Decreasing when I'm going downhill. Now in pink, I am decreasing between my local max at negative 0.31 down to my local min at 0.364 and union of sets from my local max at 2.198 on to positive infinity. It is positive above the x-axis, or y equals 0, the x-axis. So it is positive from my 0 at negative 0.778. It stays positive until my other 0 at approximately 2.92. It is negative from negative infinity to my first 0 at negative 0.778. And union of sets up to my second, from my second 0 at 2.92 on to positive infinity. Negative below, positive above the x-axis. End behavior as x approaches negative infinity. My left arrowhead, f of x also approaches negative infinity. My right arrowhead as x approaches positive infinity, f of x approaches negative infinity. And the graph, I used a function on my calculator to trace along so I could plot my points as I went. So once again, I'm going to switch over to my calculator, put in my function, plot, and for numbers 4 and 5, I'm going to go ahead and write the answers down. So I want you to pause the video, do those on your own, and then come back and see how you did. So here we have problem 4, increasing in pink, increasing in green, decreasing in the pinkish red. Zeros as listed at negative 2, negative 1, 1, and 2. Local minima at negative 1.58 and negative 2.25 for x and y. And similarly at positive 1.58, negative 2.25, and then a local max at 0, 4. End state behavior as x goes to negative infinity, f of x goes to positive infinity, and when x goes to positive infinity, f of x goes to positive infinity. And our last problem for the day, again, utilizing that calculator as a good tool to find our zeros and our local max and min, and then we can see where we are increasing, the areas in green, and we are decreasing the portions of the graph in pink or red, and then the areas where we are positive above the y equals 0 line, x-axis, and where we are negative. And our end behavior, this is an odd degree function, so we know that they're going to be opposites. We're going to have a negative on the left, negative infinity on the left, and we're going to go off to positive infinity on the right. So please make sure to work through how to operate that calculator to find those local max and mins. Remember, they are under the math functions. So on your calculator, under calc, you will see zeros, mins, and maxes, and of course being able to graph and table. And that is it for day 2.